suppose the data generating process is and beta 0 is the true value of parameters. And given the data yi, xi, we set up the empirical model. This is the error term. And we want to estimate beta. We want to estimate beta 0 from the data. And we can use OLS, ordinary least square estimator, which choose the beta to minimize the sum of square error. So our objective function is to sum of square errors, which is equal to beta xi, and I'm going to divide it by n. This is the same as without dividing n. So our objective function is minimize, choosing beta to minimize this criteria. And under our regularity assumptions, we can show that our estimator, let's call it beta hat, the OLS estimator, converge in probability the true value, the unobserved true value. In particular, where the assumption that the error terms EI is uncorrelated XI. That's the key assumptions. However, you want to note that this does not mean our starting point, minimizing the sum of square errors, is correct. We may be lucky we're starting from a wrong criterion. In the end, we arrive at an estimator that converge to the true value in probability as n goes up. If we carefully look at this criteria, sum of square errors, we are going to find that this is actually stochastic. Qn is a random variable. It's a stochastic. And in a sense that this is not so good, because whenever we have a new random sampling, then we end up in having a different criteria. And we minimize this different criteria. It's not clear why this is good. Okay, so now what I want to do is I want to show that this is indeed a good, this minimizing sum of square errors indeed a good criteria to minimize. Okay, to do so, I'm gonna rewrite this sum of square error as this. I'm going to add beta 0 xi. The beta 0 is the true value of the beta, and plus the same term, so it doesn't change. Beta 0 minus beta xi. Okay, before that, note that the true data generating process is what I is beta 0 xi plus epsilon I. So we can look what I minus beta 0 xi is actually equal to epsilon I. So this is equal to epsilon I. Qn. By the way, I'm using a subscript n under the Q to denote that this sum of square error really depends on samples of samples. I just expand this sum. And now we want to note that the low or large number will say that this is the average of n random variables, independent and identically distributed random variables. It converges in probability to its expectation. So 1 over the first term here, let's call it term 1, term 2, term 3. So let's look at these 3 terms separately. So term 1, which is 1 over n, will converge in probability by weak low or large number to its mean. And this, by assumption, is equal to the sigma squares. So sigma square is a constant. It's not stochastic. Second terms. Again, this average, these are random variable. So this epsilon I times xi is a random variable. Average by the low or large number, it converges in probability to its mean. And our assumption says that epsilon I is uncorrelated with xi. Or xx is exogenous, so this is 0. So this converge in probability to 2 beta 0 minus beta times 0 is 0. So the second term. Third term. And again, low or large number suggests that these terms, the average of xi square. Note that xi square is a non-negative random variables. We need this to converge to a terms. Let's call this phi, or maybe let's call this a. And probability, which is equal to exi squared. And note, so now there are two possibilities here. A could be positive. This is what we want. This is what we need. If A is 0, then we're going to say that there's no variation in x, right? In my particular example here, I only have one exponential variables x. So here, if a is equal to 0, then there's no variation in x. For example, possible is that yx, so y is equal to 1, x equal to 0, 2, 0, 1.4, 0, always equal to 0. Then there's no variation. The sum of the square is equal to 0. Or if we have multiple exponential variables, multivariate regressions, then a is 0. If we have this xi, they are multicollinear, then we might have this situation of a equal to 0 here. Typically, we are going to have this a is positive. And looking at xi, because the term is xi squares, so it should be quite reasonable to assume that a is positive. I hope you agree. So these converge in probability to beta 0 minus beta square a, where a is positive. Okay, so now we have Qn. Three terms, they converge in probability to non-stochastic terms. So in the end, the Qn converge in probability to, let's call this Q, which is one term is sigma square, second term is 0 disappear, third term is plus a beta 0 minus beta square. And also observe that this convergence is uniform, does not depend on beta. Okay, this convergence in probability does not depend on beta. So it's uniformly over beta. And clearly, by looking at this Q, which is no longer stochastic, is a deterministic criteria, we can find that beta 0 minimize Q. Beta minimize Q at the true value beta 0. And when we are doing OLS, we are choosing beta to minimize Qn. So in a sense that we are minimizing a wrong criteria, which is stochastic, in a sense it's bad. However, fortunately, we know that this criteria Qn, now we show that under our assumption, our regularity assumption, this criteria Qn converge in probability to Q, where beta 0 is minimized. And this convergence is uniformly over all beta. So despite that we are minimizing a wrong criteria, in the limit we are fine. So indeed beta converge, and this put hat on top of it, converge in probability to beta 0. And in this sense, the OLS minimizing the sum of squared errors is fine.